Hi everyone, welcome back. Today we'll be talking about probability density functions. I think this is a really cool part of Math 104. Essentially, a probability density function is a special function, has a couple key properties. First of all, not super important, it has to be positive, or at least non-negative, it can equal 0 at some places. And the second one, the most important one, is that when you integrate this function over the entire number line, right, so from negative infinity to infinity, this has to give me 1, right? So the area underneath my function is equal to 1. And I like to think of this as like 100%, okay? So this is 100% symbolized as the number 1 here. And if you restrict this, then what you can say is you can chop this function up into little pieces, right? So let's do it between a and b, for example. What this says then is that the probability of measuring your x value between a and b, so you write it like this, x is between a and b, is simply equal to integrating the function between a and b. Okay, so if my entire area is equal to 100%, I can chop this up into a portion between a and b, and this might equal 0.2, as in 20%. It says that I have a 20% probability of measuring my x variable to be in this little window. Okay, so it's a super cool property that comes directly from the ability to integrate a function to be equal to 1 over all space. So I will note at this point we're making use of what's called an improper integral, where you have infinities in your bounds, or at least some sort of discontinuity involved. So if you haven't seen this before, I'd recommend going and watching an improper integral video. But I'm going to throw this underneath the applications of integrals section here. Okay, so whenever we talk about probability, we also have a notion of a median and a mean as well, so we can define those. The mean is a little bit tricky to comprehend, but I'll give you the formula. The mean, let's give it a name, we'll call it mu, is equal to x times f of x dx integrated over all of space. So we've seen something like this before in centers of mass, right, where this x comes out in front when we're looking for the x coordinate of the center of mass here. Essentially what it's doing is it's assigning more value or more weight to higher value x's, right? So if I'm multiplying my function by x is equal to 1, which is, right here maybe, then it's only going to assign a weight of 1. But if I'm multiplying it by 10,000 over here maybe, we say that that value counts more, and to do so, we multiply it by x in the integrand. If the explanation doesn't make a whole bunch of sense, that's okay. What's important is you remember the formula. And then the median, we remember the median to be the exact middle of my distribution. So it's, the number of things on the left is equal to the number of things on the right. In elementary school, you remember tallying stuff off in a set of numbers, right, to find the median. Essentially what we do here is we say that the median is the point m, so m and mu different, such that the integral from negative infinity to m of my function is equal to the integral of m to infinity of my function. And it doesn't look super fun to be solving integral equations, but we also know that each of those individually should equal 1/2, right? So I'm trying to split this directly down the middle in terms of number of things. So these are my equations that I have. Okay, so hopefully, everything's making somewhat sense right now. I think it's helpful to go through an example. I prepared kind of a giant example where we're going to go through with the same function, and we're going to kind of build it up and find all of these different variables here. So let's go ahead and do that. Let's say that f of x is equal to some constant c times e to the minus 2x is a probability density function, and I'll restrict it to be positive, so or non-negative, where x is between 0 and positive infinity. And so my first part here is I need to figure out what c is. This is a really common Math 104 problem, at least in the past. So what you do when you find c is you make use of this property right here. You say that it has to integrate to 1. So essentially what I'm doing is I'm normalizing my integral to be equal to 1 over my entire bound. So I set this up. I say that 1 is equal to the integral of c e to the minus 2x dx, and then not from minus infinity to infinity, but on our bound, right? I'm going from 0 to infinity. What I like to do, I know this c is going to be a constant, right? So I can factor it out, and essentially just do this. 1 over c is equal to this integral, and then I don't have to worry about it at all until the very end. So I can just go ahead and solve this integral on the right-hand side. And what this ends up giving me is minus 1/2 e to the minus 2x evaluated from infinity to 0. And then I'm going to make this positive by flipping the bounds. Not super necessary, but I find it helpful. And then we're essentially, with improper integrals, we're taking a limit instead of plugging in infinity, right? But it's essentially the same thing. So I have 1 over c is equal to 1 over 2 e to the 0, right? So that's when I plug in 0. And subtract off of that the limit as b approaches infinity of 1 over 2e to the to the positive 2 times b. And we know that as b gets really, really big, e to the 2b gets super big. So this entire term goes to 0. E to the 0 power is just 1, so c must be equal to 2. Okay, so this is just, a quick review of taking limits and some properties of the exponential, but hopefully that wasn't too difficult. So now that we have c, we have our entire probability density function, we can start to actually find probabilities, right? So let's go ahead and do find the probability that x is between a few different numbers. So let's do between 1 and 2. Say the probability that x is, between 1 and 2 of this. And so what we need to do here then is we make use of this property here, this one, that the probability of measuring two variables is simply, the probability of measuring x between two endpoints is simply the integral of the function over those endpoints. So what I end up doing then is I say that the probability is equal to the integral of 1 to 2. My probability density function was c e to the minus 2x, but I found c, so I can make this 2e to the minus 2x dx. And I can go ahead and do the integral. It's very similar to the one we just did, except you're not taking any limits. What you end up getting is you get 1 over e squared minus 1 over e to the 4th. And what that is about equal to is 11.7%. Okay, so this is saying that if on my function, which looks something like this, right? Comes down here, I can go between here and here, 1 and 2. This area itself is equal to 0.117. So that says I have a 11.7% chance of my variable landing in this interval somewhere. And again, this is all made thanks to the fact that the integral of the entire function is equal to 1. Okay, so those are, two very typical problems for finals. Other ones are finding the mean and the median. So let's go ahead and find the median first, because I think that's generally simpler. The median, again, is this property here. So what we're going to do is we're essentially just going to pick one of these integrals to solve and figure out exactly which one looks easiest. Let's go ahead and set them up. So I have the integral from negative infinity, but we say that's just 0 in our case, right? Of 2e to the minus 2x dx is equal to the integral from m to infinity, 2e to the minus 2x dx must be a half. It really doesn't matter. The 0 here is helpful, so is the infinity. I'm going to take the second integral and go ahead and work with it. If you'd like to work out the other one and see if you get the same m value, that's a good exercise. But what happens here is that I have 1/2 is equal to that integral. So it's 2 times minus 1/2 e to the minus 2x, evaluated from infinity to m. I'm going to cancel some stuff, write stuff in a different form, and make it positive by switching the bounds. So I'm going to have this is equal to 1 over e to the 2x evaluated from m to infinity. We know what happens at infinity, right? So I have a half is equal to 1 over e to the 2m minus the limit as b approaches infinity, 1 over e to the 2b. Again, that's 0. This tells me that 2 is equal to e to the 2m. If you do a little bit of math, you get that m is equal to a half times the natural log of 2, which is also equal to the natural log of square root of 2 by some properties here. Okay, so if we actually do this out, we'll do the decimals at the end. Let's find the mean first, because there's a point I want to make. Here's our median, natural log of root 2. That says that if I were to take my function here and stop it right at this m value, right? So x is equal to log root 2. I'd have half of my things, right, on this side and half of my things on this side. Okay, it's different than the mean in the sense that it's not necessarily, it's a measure of central tendency, but they're measured in different ways. Okay, so the mean then, find mu. Mu we saw was equal to the integral of x times f of x dx, right? So the last property we're going to use is this one here. And so this gives me 2, let's write it all out, 2x times e to the minus 2x dx from 0 to infinity. And essentially this boils down to an integration by parts, right? So we have this x term here. I can let u is equal to 2x, du is equal to 2 dx. And then I can let this right here be my dv, e to the minus 2x dx. And if I integrate upwards, I get this is equal to minus a half e to the minus 2x. I'm going a little fast here because you've seen this before. And essentially what we get here is you do all of these integrals, you get minus x e to the minus 2x minus 1/2 e to the minus 2x evaluated from infinity to 0. So I'm skipping the integration. That's a good exercise to do though. So again, I'm going to make this positive by flipping the bounds. This is x e to the minus 2x, which I'll write like this, x over e to the 2x plus 1 over 2e to the 2x from 0 to infinity. And again, this is just plugging stuff in. So when I plug in 0, this goes away. And I have 0 plus 1 over 2e to the 0. That's when I plug in 0. And then subtract off of that when I plug in infinity, which is essentially a limit, right? So I have b over e to the 2 times b plus 1 over 2e to the 2 times b. There's no discrepancy here, right? This term clearly has to go to 0 when b goes really, really big. What's important to note here, and we'll get into this more when we talk about infinite series, but essentially, as b goes to infinity, sure, the numerator is growing, but it's growing at a much, much smaller rate than e to the 2b, right? So when b is equal to 3, for instance, I have 3 over e to the 6th power, and e to the 6th power is gigantic already. You can even imagine 10 over e to the 20th, right? So these are getting super, super small. And we'll talk about that again later, but essentially we can say that this goes to 0 because the denominator is growing much, much faster than the numerator. Okay, so this tells us then that mu is equal to 1 over 2e to the 0th, which we know to be a half. Okay, so let's go ahead and talk then really quickly about the median versus the mean. So we said the mean was equal to a half, whereas the median we said was equal to the natural log of root 2, which is, I wrote it down somewhere, yeah, 0.35. Okay, so a couple questions that are raised then is, in particular, why is the mean not equal to the median? in this particular case, and then also why is the mean greater than the median? And so, it's not exactly obvious, but what we can do is we can look at the shape of the function, and we can kind of figure out if it's skewed one way or the other. So let's look really quickly. E to the minus 2x looks like this, right? So it jumps down super quickly. But what we have is a bigger area underneath very small numbers, right? So what this corresponds to in the list is that I have a lot of really, really small numbers. So if I go back to like fourth grade or something, I could have a list that looks like this: a bunch of ones, a few twos, a 3, a 5, and then maybe like an 11, an 82, and then like 10,000, for instance. If I find the median, right, I can cross off all of this to get my median is equal to 2. But my mean is going to be much bigger, right, because I have this 10,000 in here. So I have 10,000. Let me do this cleaner. My mean is going to be 10,000 plus a bunch of other stuff divided by, I don't know, maybe this is like 10 numbers. I know it's probably more. But this is going to be on the order of like 1,000. Okay, this is extremely exaggerated, but this is to say that when you have a lot more smaller numbers like this, when there's a lot more data on the left-hand side here, and your function kind of tails out to infinity on this side, you still have to count these gigantic numbers in with your mean, which pulls it up quite a bit, but they get canceled with a bunch of smaller numbers down here when you're talking about the median. Okay, so this is a quick stats lesson. It's not super relevant to Math 104, but I did just want to let you know you don't have to have your mean and your median equal. So if they don't, it's not like you did something wrong in the exam. It's just simply that you're working with a function that is skewed to the left or to the right. Okay, so I know this was a lot. Hopefully it made sense. There's some good exponential lessons in here as well. But I hope this was a good review of probability density.